new Cube video. In this video I again explain you some internals of Cube library. Namely, I will keep explaining the mechanism of clustering, which we use to compress amount of recorded data in a case we store performance of iterations. So in a previous video, actually in two videos, one is linked here, I demonstrated you how to enable measurement in Scorpii for some loop of interest, and how to resolve individual iterations, and how to enable clustering or disable clustering, how to obtain the actual measurement which resolves the performance data for individual iterations in a loop. In another videos about two standard plugins like heat map and bar plot, I demonstrated you the way how we visualize this performance data, which enables you to analyze behavior of your loop, of performance data, or of performance of your loop, whether it degrades with iterations, whether it has some regular pattern, and so on. That two standard plugins of CubeGUI, heat map, and bar plot do allow you to actually perform such kind of analysis. And in this video I go a little bit deeper. I show you how the algorithm is actually working, how does it look like in a resulting profile cube file, namely in XML, anchor.xml, how these mappings do work, and so you perhaps be able to implement your own decompression algorithm, which allows you to reconstruct the original call tree out of the clusters, basically. So how does it look like for the user? So let's go into terminal first. Let's see here. So we have our terminal, and I start example of our CubeGUI basically, and I open one example of measurement where iterations are recorded. So this one, that is the typical BTMZ benchmark measurement. We see a standard set of metrics. It's the raw measurement, so basically it's profile coming directly from Scorpii. It's not remapped or post-processed anyhow. So that's basically the data which you collect. And if we take a look at the call tree and expand it, so we see the regular and the call tree of BTMZ benchmark, and we see here the region of our interest, or basically loop, which is marked as a loop, and it has 200 iterations. So if we expand it, we actually don't see these iterations because CubeGUI collapses them back. So it doesn't resolve iteration, it shows you only resulting aggregated sub call tree with aggregated performance data. You can, of course, study every individual iterations, because that's exactly what is stored in a file. So for that we go in the context menu, show iterations, and here we see every single iteration with corresponding sub call tree. And in this case we see 200 iterations. For some performance analysis, one needs to see individual iterations, or maybe some group of iterations like first 5. And so for another analysis, you don't need such kind of resolution, so you need just the whole amount, whole data. So for that, one keeps this layer in call tree hidden, and one aggregates the actual performance data. And actually in this display, where the iterations are collapsed and hidden, the plugins barplot and heatmap actually do have sense, and that's exactly what I demonstrated you in another video. Okay, so we can take a little bit deeper look. So if we go into info, we see actually some information about this measurement, and we go into global information. Here are global mappings, attributes are displayed, some global information about this measurement, and we see that this measurement clustering has been enabled. So we see 200 iterations. We have this technical mapping, which you will understand hopefully by the end of this video. And we see down there that we have been using 16 clusters only to actually describe performance of this measurement or of this benchmark. And we see, for example, 122, that is actually ID of the loop which has been clustered. So here is 122, here is 122, that is this the region which is marking our loop. Okay, so that's how does it look like for the user, but we would like to be developer, not user, basically to take a closer look how does it look like inside of the cube. So before we proceed, I remind you to subscribe, to share this video with anyone who is interested. If you have any comments, write them below in the questions, write them below in the comments, and of course give us a like. Alright, so let's go to our notes where I will try to explain you in details how does it look like. So let me see how it is working here. Okay, so we start recording. Alright, okay, so clustering algorithm. Clustering. So very first and main thing which one has to keep in mind or know is that clustering algorithm is used to when one does measurement of iterations of a loop. Why? Because it is known, expected, kind of understandable that performance data or performance, how does it look like in numbers, visits, timings and so on, does not really differ from iterations to iterations really much. So the iterations, they do behave usually very similar. Maybe there are some ifs and what so or some another branches within execution of a loop, but in most cases the iterations are very similar from the performance point of view. So therefore is actually we resolve iterations, but we do not need so much data. Let's say there is a lot of redundancy, and therefore we actually store not the actually individual iterations, but we try to cluster the performance behavior, and then we store in the end clusters of the data, out of which we then can reconstruct the whole loop. That is the main idea. So okay, let's write it down. It's used for measurement of the performance of individual iteration of loop, of some loop. And because performance data, so let's have it a little bit different in the sense of coloring. Performance data is similar therefore we do clustering. So basically clusters are nothing else than just a region of similarity in such abstract space of performance data. So what do we actually do? The idea is we replace a lot of individual iterations by the corresponding cluster. And because we have number of iterations, usually much more than number of used clusters, or this similarity blobs, we do gain or we reduce the number of required memory and file space and so on. So we actually do have number of iterations, can be thousands, 20,000, 100,000 of iterations, but because they all similar, they actually need only m clusters. So therefore m way smaller than n, and we have data reduction, so therefore without actually losing the information about performance behavior, because let's imagine we have a metric time and all iterations are going 1 second, 1 second, 1 second, 1 second, then maybe some change in 20 seconds, then 20 seconds, then back to 1 second and 1 second. So it's important to know that there was this jump, but that the fact that they are all 1 second, you don't actually need it. You can store only 1 second as a cluster, 20 seconds as a cluster, and again 1 second as a cluster. So actually 2 clusters. And then you say cluster 1, 1, 1, 1, 1, and there is cluster 2, 2, 2, 2, and then 1, 1, 1, 1. So we could actually describe whole behavior of such a loop using only 2 basically clusters. So that's the main idea in this data size reduction. So we call it size optimization or something like that. Size size optimization is meant of used memory, of the used file space, of used amount performance data. So how does it look like in detail? So that's the main idea. So let's go to another page. How does it look like in practice? Okay, so let's play just like mental scenario how that would look like. So we have the execution of our program, some benchmark, and then we are running into the loop which we have been marking in a Scorpy as a loop where the iterations have to be resolved. Take a look in another video. So let's see, we have for example 4 locations, MPI pure MPI measurements. We have 4 locations which might be ranks 0, 1, 2, 3. So we have then iterations it 0, and it has some subcall tree. In this example we will keep it as a identical subtree. If it is not identical, one should understand it as one should expand it to the smallest the subtree which contains all possible subtrees in this measure. So basically one unifies them to one common big subtrees, and where elements which are not present in some iterations, they are zeros. Yeah, so let's see, we have here foo, and it has 2 subcalls, bar 1 and bar 2, right? So kind of such a table, and we have location 0, location 1, location 2, location 3. So basically MPI rank 0, MPI rank 1, 2, and 3. And let's say we have performance data. So that might be metric time. So we actually I have to move it a little bit slower, like this. Okay. So we have performance data. Let's say it is 10 seconds. Here we spend 5 seconds. Here 3, 2. Here is like 11, 5, 4, 1, 10, 5, 3, 2, 11, 5, 4, 4. That will probably not work. Let's see. Let's do here 9, 9. So this is inclusive data, basically. That's why every parent has to have actually bigger values than the children. Okay, and then this iteration is finished, then we go to another iteration, and then we have another performance data, so iteration 1, it has the same call tree, foo, bar 1, bar 2, and let's see, it has, let's say 11, 3, 1, 1, then 8, 5, 2, let's say, so 11, 5, 4, what is that, 5, 4, so let's do 6, and 2, and here we have 11, 3, 1, 1, something like that. And then we have another some iterations, and let's see the iteration, the last one iteration, how it is typically and we have here foo, we have here bar 1, bar 2, and let's see 10, 5, 3, 2, 11, 5, 4, 1, 11, 9, 4, 4, 10, 10, 8, 5, 2. Yeah. Okay. So this is our performance data. Of course, it's a little bit made up, but nevertheless, we see already from this data that the data within for every call tree, for every location, actually very similar. So if we just take a look into it, we see that, oops, that we didn't want to do. We wanted to do something like, I don't know, wanted actually to cut it. Check, delete. No. Okay, will not work. Okay, then let's do like this. So, so we actually see that they are very similar, so we can build up a cluster. So what kind of clusters do we have? So we have clusters, and we have to do like iteration 0, iteration 1, that has own basically performance data entry. So therefore we have to actually mark it somehow. So iteration or instance, and then we have foo, we have bar 1 and bar 2. So what kind of clusters do we have? We have cluster 0. So that is the 10, 5, 3, 2. 10, 5, 3, 2. The cluster, another cluster, 11, 5, 4, 1. So that would be cluster 1, 11, 5, 4, 1. The next one, 10, 5, 3, 2, it's already there. So it's another one, 11, 9, 4, 4. So cluster 2, 11, 9, 4, 4. Then we go to iteration 1 or location 0. So what is this? 11, 3, 1, 1. So we didn't have it yet. So, okay, 3, 11, 3, 1, 1. Then 10, 8, 5, 2 we didn't have. So it is 4, 10, 8, 5, 2. Then we have cluster 5, 11, 6, 4, 2. 11, 6, 4, 2. Then we have 11, 3, 1, 1. We have recorded it. It is cluster 3. Then 10, 5 in the last iteration, location 0. So 10, 5, 3, 2. We have such cluster. 11, 5, 4, 1. We have such cluster. 11, 9, 4, 4. We have such cluster. And 10, 8, 5, 2. We have such cluster. So we obviously need 1, 2, 3, 4, 6 clusters to describe all performance data, and actually pretty much exactly. Yeah, so because we made it like that. How does it look like in practice? So we have six clusters. In order to store them in our Cube performance model, we actually can use the same number of locations, and we can use the the call tree as a dimension. So if we keep the same number of locations, which we do, so these are 4, then we need only basically 2 clusters. It's not anymore this cluster, it's like 2 instances which we store inside of the cube where we describe clusters. So how does it, what do I actually mean? So in cube, we would store them in a call tree, not anymore iteration 0, I will store instance. And this instance of subtree. So that will look like, let me write it. So we replace iterations by clusters. So and we have to store 6 of them. So we store our call tree, how it is normally is going on, and then when we enter the loop, we do not store every iteration, we store instance. And because we had only 4 available locations, we have to have 2 instances, each of them 4, so in total 8, right? But we don't need 8. So we write here in 0, it has 4 foo, it has bar 1 and bar 2, and then we have instance 1, which has foo, which has bar 1 and bar 2, and pretty much that's all what we need. And then can go remaining call tree, which is actually after the loop. So there are no anymore any iterations whatsoever. This part of the call tree is that what is under the loop, or later in the call tree under the loop. So what we actually store here, so we can store here, we keep calling it locations, although it is not anymore locations in per se, it is cluster. So, but I will call L1, L2, L01, L2, L3, because in the terms of cube, and we actually store them there. This data, pretty much this matrix. So we store in location 0 for instance 1 these numbers 10, what's there, 10, 5, 3, 2. In location 1 we store 11, 5, 4, 1. In location 1. In location 2 we store 11, 3, 1, 1. And in location 3, let me see, we store actually I had to store basically this way, 10, 5, 3, 11, 5, 4, 1, 11, 5, 4, 1, and this here 11, 9, 4, 4, so that should be 11, 9, let me remove it, 11, 9, 4, 4, and in the third one would be 11, 3, 1, 1, so 11, 3, 1, 1, and then because we still have more clusters, we actually create another instance, 1, and then use these available locations as to store this, and the remaining clusters that would be then 10, 8, what was that, 5, 2, 5, 2, and here 11, 6, 11, 6, 4, 2, and this we fill simply with zeros because we have to have some data. And that is what we store in a cube file. We this data is actually then stored in a file, and instead of having here n iterations, each of them 4 locations, so n times 4, we reduced it to 2 times 4. Of course, this example, not forget, is based on this 3 iterations, 0, 1, and n. It's assuming that all data within between 0, 1, and n, somewhere there in all these iterations, is also similar, so basically consists out of these clusters. If one has a data, one has to introduce so-called deviation, where how far you are allowed to be from the cluster in order to be still described by this cluster. Yeah? So in the praxis, if the deviation is too far from every cluster, it produces new clusters, and as soon as we run into limit our cluster, so for example, we set in the settings we would like to have maximal 16 clusters. So the measurement is going. Every time we are a little bit off the cluster, we create new clusters, or if we are going over threshold. Otherwise, we describe the iteration by some cluster, otherwise we create more clusters. And then later on, if the measurement is going, we collapse the similar data and creates then another cluster by increasing this basically similarity threshold. So in the end, we end up with 16 clusters which we set up as a parameter, and they are, let's say, as far from each other as it is possible while still describing the performance data. Okay. What's that? No, I don't want to do that. What is that? Why I am doing this? No, I don't want. Okay, I don't know what I did here. Why I am here? No. Okay. No. Okay. So that is the our data which we actually stored, but that is not enough. We have in the end n iterations and not 2 clustering. We have to be able to reconstruct our original call tree with n iterations and fill it with data based basically on these 6 clusters. So how does it look like? It means we store additionally to our call tree and performance data mapping table, where we actually do something like that. So we actually write literally, we name the iteration like zero, and for every location of this iteration we have to choose cluster. So basically cluster, that is the only one sub call tree. So for location 1 can be different clusters than for location 2 and so on. So therefore we write such mapping where we describe iteration 0, and iteration 0 consists out of 10, 5, 3, 2, 11, 5, 4, 1, and so on. And these are, I will write it like that. This is location 0, 0, which means it is iteration instance 0, location 0. So iteration 0 in its location 0 is described by the instance 0 for location 0. Then location 2 is described by what is that? 11, 5. That is the instance 0, location 1. So our location 2 here 10, 5, 3, 2 described again by the instance 0, location 0. So it is location 0, 0. And the last location L3 is 11, 9, 4, 4 is described by instance 0 but location 2. So that's why we have a location 2. Okay. So this mapping for iteration 0 describes completely the part with all subcall tree of this performance data for iteration 0. For iteration 1, that would be, let's take a look, 11311, that is iteration instance 0 iterations location 3. 10855, that would be 10855 or 52. 52, that would be instance 1, location 0. So we write it location 0. For this iteration 1, location 2, it's 11642. This is described by 11642, that is instance 1, location 1, right? And the last one, 11311, that's again 03, so L03. So then we have another iterations and the remaining n is, hopla, I'm writing faster than I'm thinking. So here is 10, 5, 3, 2, that is our L00, 11, 5, 4, 1, 11, 5, 4, 1, that is L01, our 11, 9, 4, 4, 11, 9, 4, 4, that is L02, and 10, 8, 5, 2 is actually 11 location 1, 0. And let me frame it. This is our mapping for the clustering, and these are our clusters. So if we store this data inside of cube file, this mapping, this performance data, and we have to store like our iterations root is equal, let's say 100, this info, then we are in position to reconstruct our iterations call tree with all individual call trees and fill it up with the performance data, having only this stored data of clusters, mapping, and where it is actually. And this we do for every metric, so therefore we can reconstruct the original, let's say, not clustered view of the performance. So how does it look like in reality? I want to show you also internals of cube file, where you see actually all these things and understand how it is looks in reality. Before I do it, I remind you to subscribe, give us a like. If you have any questions, put them into comments, and of course share this video. So let me do here this. Alright, so let's go to our terminal again, and we here. Alright, so let's take a look first again in the cube, and very same cube file. What we find here, we see that's our basically loop with all this collapsed call tree, and then if we go into the info, into this global information, we see here exactly what I just made. We have 200 iterations, so we know how many iterations we have to recreate while recreating the call tree. And for example, we see the cluster mapping one. These are ID of instances. So this instance 1, instance 2, all this call tree, they have IDs inside of the cube. So therefore we, instead of having yet another numbering, we just use directly IDs of the elements inside of cube. And that is how it is here described. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So then there are another clusters, and one describes it all the way for all 200 clusters. We have 16 clusters, so that we know how many of them, and we have that is this iteration root. That is how it looks like in this view. If we go then into the our example of the, here is our profile. Here it is already expanded because it is in the end nothing else than tar archive. And here is this Anchor XML is listed separately, so we can open it actually using some editor. And what we see here, we see that in a global part of the Anchor XML, I have been describing in another video how the syntax of Anchor XML looks like. Just take a look in the very same playlist. So we have global attributes, and we see here root node ID 122, number of clusters 16, number of iterations 200, and cluster mapping is also performed via these global attributes as comma separated values of the IDs of corresponding instance. So how does it look like further? So we have here a metrics description, then we have regions. Every region of cube is described in the XML part, like here, for example. we have in this sense instance as a region and of course all call tree. So let's take a look further, a little bit deeper. Tick, tick. We have this ID, and here we have instance, these instances. They are recorded as regions because we are going to refer them then directly. And then later on we have here the call tree, which is, one has to study it. Somewhere here is the call tree, because nesting is not, you don't need to store nesting inside of XML file if it is being parsed anyway. Somewhere here is this instance 1 and instance 2 are recorded as a individual sub call trees. So that like if we go to our, let's see, CubeDump, so it has two command line options. I will describe CubeDump a little bit later. -w displays our basically, no, let's skip the paging. Oops. Here it describes the metadata of the cube file. So we can dump the data, or we can dump the description of the dimension. So you can see it is a little bit more human friendly. So the metrics are described. Here is the region list, and we see that in the region list we have instances and we have iterations as regions entries, and then we have our call tree. And here if we search we see, like, for example, iteration 1, and then there's a call tree. If we just keep searching, iteration 2 and call tree, because library, that's the library which does actually this reconstruction. Another command line option of CubeDump is additionally -y. It actually disables declustering, so disables this reconstruction of call tree of iterations, and displays exactly call tree which has been stored inside of profile CubeX. So with all this instance 0, instance 1. So let's take a look here, and then let's take a look of, we see here in a list of regions, we don't have here any more iterations. We have only instances. And then if you take a look here, we do not have iteration 0 blah blah. We have instance 64, we have instance 63, and so on. That is how that is stored in the end in a cube file. Okay, I hope you understood more or less details of the clustering algorithm and how does it look like in a praxis, and how does it look like in a result. And perhaps you will be then capable to implement your own declustering parser algorithm, or maybe you will be capable to find some bugs and fix them for Cube library. All patches are welcome. Anyway, I hope you like this video. Give us a like. If you have any questions, put them into the comments, share, subscribe, and see ya next time. Bye bye.